our seminar here. Okay, please join me in welcoming Sarah Smith. A little bit of background: Sarah got her undergraduate degree in English and anthropology, then spent 6 years working on environmental projects for UNEP and UNESCO in Indonesia and South Africa, part of which included living in the bush in rural South Africa for 3 years, which is really cool. Upon returning to the States, Sarah got her master's in climate and society from Columbia University, followed by a postbac in physics and math before joining the Department of Earth and Environmental Sciences PhD program. Sarah is now a fourth-year PhD candidate working at Lamont with Ming Fontaine and Yu-Tian Wu on understanding the seasonality of Arctic aerosol processes. I just want to add, on a personal note, I've had the privilege of being Sarah's classmate for the last 2 years. I think you'd be really hard-pressed to find someone as dedicated and passionate as Sarah when she pursues anything, from pedagogy, her own research, or just increasing her general knowledge of earth science. So before I pass things over to Sarah, 2 quick notes. As I said, we're recording today's seminar, and I'm going to request that we hold questions for the end of the seminar today. So take it away, Sarah.
Well, thank you so much, Maggie, and thank you everyone here for having me. I'm gonna talk today about some things I've been thinking about for the last few years, focused primarily on just improving our observational constraints of aerosol seasonality in the Arctic. So just a little bit of background. Aerosols, of course, can affect the radiative balance either directly by reflecting incoming or reflecting or absorbing incoming radiation, or by seeding clouds, which can have their own effects. From the AR6, the best guess we have for the effective radiant forcing for all aerosol processes is negative 1.3 watts per meter squared. When you compare that to their ERF for CO2, you see that it's a little bit more than half of the global forcing. So aerosol forcing can be substantial, but it's also characterized by a lot of uncertainty, which makes constraining aerosol radiative effects both interesting and really important. In the Arctic, we have actually even more uncertainty for aerosol radiative effects, and that's because we just have really poor observational and model constraints in the region. And one of the things that we're still trying to do a better job of doing is constraining aerosol seasonality. So historically, there was this kind of idea of an Arctic haze type phenomenon where you had really high aerosol burdens in the late winter, early spring, and then a drop off in aerosol in the summer, and that's kind of the classical pattern that we expected to see. The extent to which we can constrain that seasonality is really important because in the Arctic, the aerosol effects can vary a lot from season to season, and that's because of really pronounced differences in insolation. When it's dark, of course, you're going to have no aerosol radiative effects, but also the sensitivity of Arctic temperatures to the seasonality of the forcing varies considerably by season. So a paper in 2016, for example, found that forcing in spring tends to have the greatest long-term effects on Arctic temperatures. And then finally, Arctic amplification itself shows a really pronounced seasonal cycle. So again, any type of forcing that we're talking about in the Arctic, really the question of constraining the seasonality of that forcing is sort of central to being able to define it. As far as our observations of Arctic aerosol go, most of our long-term in situ observations come from just 6 monitoring stations. These stations are not are both sparsely distributed throughout the Arctic, and they're not uniformly distributed, and that makes it kind of hard to figure out the extent to which any one station is representative of the entire region. One paper that I kind of relied heavily upon in sort of developing my motivation for this project, they looked at different aerosol characteristics and categorized the seasonality of those characteristics from 2012 to 2014 at each of these different stations. And here I'm showing you the seasonality of scattering coefficients during that time. They did tend to find that most stations kind of agreed with the sort of Arctic haze pattern of having high spring wintertime values and lower values in the summer. But 2 stations actually didn't agree with the other stations. One was at Summit, which is atop the Greenland ice sheet. It's located at 3.2 kilometers altitude. And the other was Pallas, which is located in northern Finland. It's the only station that's located in a boreal forest, and it's also the lowest latitude station. So ultimately, their conclusion from this is that when it comes to the question of seasonality, the Arctic really can't be considered a uniform region. And that kind of brought me to my motivation. So I'm kind of motivated to understand the processes governing Arctic aerosol burdens. But in order to do that, you need to know which areas within the Arctic are governed by the same processes at the same time. And then ultimately, I want to understand what data sets are useful in representing those processes. So if this was any region, any remote region other than the Arctic, I would be relying on satellite observations to kind of characterize this seasonality question. I could use aerosol optical depth, or AOD, which is a column integrated measure of aerosol burdens using the optical properties. Most AOD data sets come from what's called passive sensors. So things like MODIS. The problem with a passive sensor is that it relies on sunlight. And so that means that it can only get retrievals during the daytime. And in the Arctic, what that means is that it doesn't have retrievals, or it doesn't have high quality retrievals for a lot of the year. There's another instrument, CALIOP, which actually just retired last year, which is a LiDAR-based instrument. The LiDAR allows it to get retrievals during the nighttime, but that still doesn't actually help us as much as I would like with the kind of seasonality question, because there's slight differences in the way that nighttime and daytime retrievals are processed for CALIOP, and you really have to treat each data set, the daytime retrievals and the nighttime retrievals, separately. That said, because of the viewing geometry of the daytime AODs, we can actually get a gridded AOD product in the Arctic up to about 72 north year-round. So that's something that we can use to help us understand at least low Arctic seasonality. And then the CALIOP, because it's a LiDAR instrument, has the additional advantage of providing a vertical profile, which can give us some insight into the region. So my first kind of section that I want to talk about is sort of characterizing subregional variability in the Arctic. The first thing I want to ask is whether the daytime CALIOP AODs are actually useful for contextualizing station observations in the region, and whether I can use them to characterize subregional variability. Assuming that they are, I want to see how Arctic aerosol seasonality varies both in the vertical and in the horizontal. And I want to consider that within the context of the location of station observations, and I want to see how representative stations may be of region-wide seasonality. So to answer the first question, I took absorption coefficients, which are shown in red here, and scattering coefficients from that other paper that I mentioned over the 2012 to 2014 period, and I just plotted the seasonal cycle of those two measures. And then I came up with what I'm calling the near station or near surface level AOD from CALIOP. So what I mean by near surface level, I took extinction coefficients located near that station, and then I integrated them from 30 to 500 meters just above the station. So that's kind of like a proxy for what I would expect scattering and absorption to be doing at that particular station. A few things to mention about this. At almost every station that I looked at, scattering coefficients are an order of magnitude greater than absorption coefficients. So we expect the AOD to correspond better with scattering coefficients than the absorption coefficients. And then also just mentioning that the seasonality that I'm getting from the CALIOP AODs is different from the seasonality that I'm getting from the in situ data. And that's just because I had such infrequent sampling with CALIOP that getting a seasonality from 3 years didn't give me robust enough results. So I did that for each of the 6 stations that I have data for to figure out how well the CALIOP AODs were representing the seasonality that we saw from the in situ data. I used a Kendall's tau measure, and what I found was that for almost all stations, I got a Kendall's tau above 0.5, both when I was looking at comparisons with the seasonality of AOD with scattering coefficients and the seasonality of the CALIOP AOD with absorption coefficients. The one outlier is Pallas. So this was kind of an interesting case. I'm not entirely sure what's going on here, but this is the only station where I saw a decoupling of absorption and scattering coefficients. I'm not entirely sure what was driving that, but in this case, the CALIOP AODs tended to correspond fairly well with the absorption coefficients, and neither of them really correspond with the scattering coefficients. It was also the only place where the absorption coefficients were of similar magnitude to the scattering coefficients. But overall, the thing that I was able to conclude from this is that the CALIOP AODs do a reasonably good job of simulating the seasonality that we see at stations. They're not perfect, but as you'll see later when I talk about other data sets, they're a lot better than anything else that I've been able to see so far. So then the next thing that I wanted to do was to consider how seasonality may have differences within the Arctic when I'm considering different locations in the column. So what I did is for locations near each of these stations, I took the seasonality of the total column AOD, and I plotted each of those corresponding to each station. I then did the same thing, but divided the column into the portion of the column below 2 kilometers and the portion of the column above 2 kilometers, which in practice is 2 kilometers to 8 kilometers in height. What I found is that for every station, with the exception of Summit, which doesn't have any below 2 kilometer extinction, is that we saw differences in seasonality when we compared the lower and the upper portion of the column. Below 2 kilometers, in all cases, we see a wintertime peak in AOD. And then above 2 kilometers, we tend to see a pattern where we have 2 peaks, one in around April, kind of mid-spring, and then one somewhere in late summer. The other thing that I did is I wanted to just see region-wide what sort of seasonality I was getting in the upper and lower portions of the column. And so to do that, I just took area-weighted mean AOD values for each month and then calculated the median from that. And I did that for the total column, the below 2 column, and the above 2 column case. And so I see that the Summit AOD tends to actually correspond really closely with the region-wide upper level AODs. So from this, I think it's pretty reasonable to conclude that Summit isn't necessarily different from the other stations. It's just higher in altitude, and it's reflecting differences in the seasonality at the higher levels. The next thing that I wanted to look at was how AOD may vary in the horizontal, or how the seasonality of AOD may vary in the horizontal. So to do this, I took the seasonality, the median values for each month, and I took the seasonality of AODs for each grid cell that I had within a 60 to 72 north domain. And then I applied a k-means clustering algorithm to the AOD seasonality. And from that, I was able to get 4 different clusters, and the locations of each of the clusters is shown in this plot here. And then I can also show you the seasonality that's associated with each cluster as well. So most of the clusters tend to peak in winter. The one exception is this red region, which I've been calling the fire region, which is located over the Siberian boreal forests. It does actually tend to have pretty high wintertime values, but then it has a second peak, which is driven by wildfire in the summer. The other thing that was important to me to look for is that the clustering didn't really follow a latitudinal gradient, which means that we can use the subarctic and the low Arctic region potentially to give us insight into some of the higher latitude processes. The other important takeaway, I've plotted each of the station locations here as well. All of the stations that we have that are located below 72 north tend to fall in cluster 3. And cluster 3 is our lowest amplitude cluster in terms of the seasonality. Cluster 1 represents just about as much of the Arctic as cluster 3 does, and it has a much higher amplitude. And we don't have any stations in that location. So overall, I think that the station data that we have is likely underrepresenting the seasonality of low Arctic aerosols. So just to kind of summarize all of that, I do think that CALIOP daytime AODs are useful for characterizing low Arctic seasonality. Aerosol burdens in the upper portion of the column are going to likely show different seasonality than lower the lower portion of the column and high altitude stations should be assumed to have a different seasonality than low altitude stations. And then in the horizontal, I tend to see less difference in seasonality than I do in the vertical. The one exception being the fire region. But again, the fact that station data underrepresents low Arctic aerosol seasonality is something that we want to consider going forward. Is there anywhere I can look at the time? Sorry.
I can just tell you, I'm sorry, 121.
Okay, good. Okay, and so that brings me to my next question, which is how useful are other potential data sets in trying to characterize seasonality of AOD in the Arctic? And I considered reanalysis data sets first. I looked at MERRA-2, which is a NASA product, and then CAMSRA, which if you're not familiar, that's the ECMWF reanalysis product. They came out with the Aerosol product in 2019, so it's relatively new. And then I also, in this case, look at AODs from different passive sensors, at least 4 of which are assimilated into the reanalysis products. So actually, this kind of started because I was just comparing the seasonality of Calliope daytime and nighttime AODs, and I had them for both the all sky case, which I'm showing in solid, and the cloud-free case, which is showing in dashed lines. I was trying to just compare them to the reanalysis AODs, and what I found was that they had very, very different seasonality. In fact, the seasonality was opposite. And I was actually really surprised to see that seasonality from the reanalysis products, because what I knew from station observations led me to think that I would expect to see something a little bit more like this. So this is just showing scattering coefficients from Barrow, which tends to be a fairly representative station. And so I kind of didn't know what to make of the reanalysis AODs at first. I wasn't sure if this bias in seasonality was restricted just to the Arctic, and I wanted to see if it extended beyond the region, and I also wanted to control for the difference in magnitude between the Calliope and reanalysis products. So to do that, I took for each Calliope product and each reanalysis product, I took the zonal mean for each latitude band in each month, and then I calculated the median value for each month from those zonal mean monthly values. And then from that, I normalized that seasonal cycle, or I normalized those monthly median values to their own seasonal cycle within each latitude band. And so what that gives me, and what I'm showing you here for the Calliope day and the Calliope or the MERRA-2 case, what that was able to give me was the ability to subtract the normalized values from one another and show you just the differences in seasonality without regard to magnitude. And so I did that for comparisons between Calliope day and night with both the MERRA-2 and the CAMSRA data sets. And what I can see here is that the difference in seasonalities are in fact evident in both hemispheres. They extend well beyond the Arctic into the mid-latitudes to about 40 degrees. And they're evident both in the comparisons between the reanalysis products and the Calliope night products and the Calliope day products, but they tend to be more pronounced when comparing to the Calliope day products. So given that I was just looking at the reanalysis products, it wasn't clear to me whether the bias and seasonality that I was seeing was coming from the sort of modeling component of reanalysis, or if it was coming from assimilation from passive sensor AODs. And characterizing seasonality from passive sensor AODs is actually quite challenging in high latitudes because you have to control for sampling biases. So here, what I'm showing you is just the number of months that I have data for MODIS within the Arctic region. And so during the spring, for example, MODIS AODs are going to be just representing the North Atlantic. In the summer, they're going to be representing a much broader portion of the region. And then in the autumn, there's a really strong latitudinal gradient. So I need to control for that. And so to do that, I took the Calliope daytime AODs, both the cloud-free AODs, which are dashed here, and the all-sky AODs, which are solid. And I subsampled the Calliope AODs to only months and grid cells where I had data available for a passive sensor, in this case, MODIS. From that, I can then calculate an area-weighted mean AOD for each month in each data set, and then find the median value, the monthly median values from that. I also just noted above each month for each data set the number of months that I used to calculate the monthly median, because I didn't want to have, for example, a January median value that was calculated from just a single month of data. So I did that for 6 different passive sensors. What I found was that 4 of the sensors, AVHRR, MODIS, SeaWiFS, and VIIRS, tend to show peaks in July. MISR and POLDER tend to show a peak in the springtime, April or May. But across the board, every single passive sensor shows a divergent seasonality from the CALIOP AODs when we compare them from September to April. So this might not seem that surprising that instruments that rely on sunlight do poorly when you don't have a lot of it. But I do want to make the point that the data sets that I use in this analysis are quality screened level 3 data sets. So that means that users are pretty much taking them as being good enough to draw conclusions from. As a data user, I think people don't always question the data that deeply. And then also, I think sometimes too, when we talk about the Arctic, the kind of idea is like, well, that's just the edge of what we know. But for people who work in the Arctic, this kind of stuff is important. And so I think if the data is being put out there, we should know what kind of questions it can be useful to answer and what kinds of questions it can be. What I don't know yet is the extent to which the reanalysis products are in fact propagating biases from the passive sensors. But given what I've seen so far, I think it's also plausible that the bias that we're seeing between passive and active sensors may be affecting the reanalysis AODs as well, and that's an important thing to control for. That said, the kind of caveat I want to give is that the extent to which the CALIOP daytime data is representing like the true seasonality and the passive sensors are representing the false seasonality, I can't really say that from the analysis that I've done so far. Which brings me to my next topic, which is the biases between different AODs datasets globally that are well known. So globally, validation of CALIOP AODs has shown that the CALIOP retrievals tend to be biased low relative to MODIS. And this is a well-known bias. The reason that it occurs is because when MODIS gets a retrieval, it's looking automatically at a column integrated value. With CALIOP, the way that it processes AODs is it segments the column into different layers, and each layer is classified as either clean air, aerosol, or cloud, and these are mutually exclusive categories. So you could have multiple clean air layers stacked on top of each other that have some aerosol, and when you consider them in an integrated way, you get some signal, but the layers themselves are considered clean air instead, and that's largely what we that's largely the thing that the literature so far has attributed to the CALIOP low bias. The other thing to mention, though, is that the CALIOP daytime AODs are also biased low relative to CALIOP nighttime AODs. And this is because the lower signal to noise ratio during the day, because of the sunlight, leads to a higher fraction of what they call undetected layers. So cases where you have an aerosol layer with very, very a low optical depth that's categorized as clear air instead of aerosol. MODIS also has biases though, and especially with regards to MODIS cloud optical depth properties, there have been a few papers that have explored the extent to which cloud optical depth can be sensitive to the viewing geometry. So in one paper, they found that MODIS liquid cloud optical depth actually increased with higher solar zenith angles. And then another paper in 2010 found that MODIS retrievals showed an inverse relationship between aerosol and cloud optical depth biases. So that all kind of led me to my hypothesis, which is that maybe the bias between CALIOP and MODIS shows some dependency on the solar zenith angle. And just for clarity, the solar zenith angle is higher when the sun is lower on the horizon and lower when it's near nadir. So to test this hypothesis, I wanted to look at level 2 AODs from both MODIS and CALIOP. So up until this point, I've only been looking at level 3 gridded products. Level 2 products are the retrievals that are used to find those gridded averages. I looked at level 2 gridded AODs from both MODIS and CALIOP. Because MODIS and CALIOP were both flying in the A train in 2010, I was able to get a really high fraction of co-located retrievals between both instruments using a pretty strict criteria. So just in a single year, I was able to get over 100,000 co-locations. And I was able to, because they both flew in the A train, I was able to control for the MODIS viewing zenith angle and only get near nadir retrievals from the MODIS instrument when I was doing that. So what we think is that all the differences between the co-locations that we saw are coming from the solar zenith angle and not the viewing zenith angle. In examining the differences, the biases between co-located retrievals, I consider two different cases. The first case is what I'm calling the relative difference bias. So this is a case where both instruments are retrieving some non-zero value of AOD for a given co-location. The reason I'm looking at the relative difference instead of the absolute difference is because there can be latitudinal and seasonal differences in AOD burdens. And so you're going to have higher absolute differences where you have higher AOD burdens. And so this helps me control for that. I also defined something that I'm calling the zeros bias. And this is a case where one instrument is retrieving an AOD of 0 and the other instrument is retrieving some non-zero case of AOD. And I partition these out from the relative difference bias because I don't think that getting a relative difference of magnitude 1 is particularly illuminating. And also because these CALIOP zeros cases are going to be, they would be characterized in the previous literature as a case where you have some undetected layer. And so these kinds of cases actually dovetail really nicely with the way that CALIOP validation against MODIS has happened previously. So looking at the relative difference bias, what I'm showing you here is just a kernel density estimate of the relative difference between CALIOP and MODIS as a function of the solar zenith angle. The dependency that we found was really significant. Our p-values were lower than our float when we calculated them, and the dependency was actually very substantial. So over the entire 20 to 80 degree solar zenith angle domain, we calculated that this dependency would account for a 67% reduction in the bias between MODIS and CALIOP. We also noted that when you're viewing it this way, the dependency looks nonlinear. But one of the things that we needed to consider when we were thinking about the relative difference was the role of MODIS quality control flags. So all of the MODIS retrievals are given a quality control flag where a QC flag, where the QC flag can range from 1 to 3, where a value of 1 indicates a low quality retrieval, a value of 3 indicates a high quality retrieval. When the L2 data are used to calculate the L3 gridded data, they're computed using a weighted mean function. So the low quality retrievals are given less weight than the higher quality retrievals. But the frequency of high versus low quality retrievals varies in space and time. And so what I'm showing you here is just by latitude bin and by month, the frequency of low versus higher quality retrievals. And so the green areas are characterized as having more low quality retrievals. The purple areas have higher quality retrievals overall. And then if you look at the Arctic specifically, you can see that from September to April, we tend to have a much higher fraction of low quality retrievals, whereas from April to September, you tend to have a higher portion of high quality retrievals. So we wanted to look at this relative difference bias and partition it into co-locations where we had MODIS retrievals characterized by high quality retrievals versus low quality retrievals. And so in the top bin, you see the same KDE, but only using high QC flag MODIS retrievals, and the bottom bin shows only low QC quality MODIS retrievals. In both cases, we still find that the dependency is significant, but they show very different magnitudes. So in the high MODIS quality case, we tend to find a 9% difference in the bias between CALIOP and MODIS if we were to integrate over the entire solar zenith angle domain, whereas in the low QC flag case, we have a much greater, near 50% reduction. I'll also mention that in the low QC flag case, a lot more of the variance is explained by this dependency, and that the dependency itself is evident even at relatively low differences in the solar zenith angle. So we see that reduction, instead of seeing kind of be nonlinear, we see it occurring even from like 30 to 40 degree solar zenith angles. So we do find a relatively robust relative difference bias, but we also think that that's mediated by the fraction of low quality retrievals that you get in September through April in the Arctic. And then moving on to the zeros bias. So in this case, what I'm showing you is using the bars. What I'm showing you is for different solar zenith angle domains. These bars show the fraction of retrievals within a 5 degree solar zenith angle domain, where I got one instrument retrieving a value of 0 and the other instrument retrieving a non-zero value of AOD. And the cases where MODIS is retrieving a 0 value are shown with the yellow bars, which mean that CALIOP is biased high relative to MODIS. And the cases where CALIOP is retrieving a 0 value are shown with the blue bars. So what we were able to find with that is that we find cases where CALIOP is retrieving a 0 value throughout the entire, almost the entire 20 to 80 degrees solar zenith angle domain. And there's not a real solar zenith angle dependence that we can draw from that conclusively. But the MODIS cases only appear beginning at 50 in the 50 to 55 degree solar zenith angle bin, and they increase exponentially with increased solar zenith angles. Cases where MODIS is retrieving a 0 value of AOD and CALIOP isn't are not documented in the literature. And everything we know about the comparison of the two instruments and how they work would lead us to think that MODIS should be retrieving in cases where CALIOP isn't, and there shouldn't really be cases where MODIS is retrieving a value of 0 and CALIOP is retrieving some non-zero value. So this leads me to think that, at least in this case, the bias is coming from MODIS, not from CALIOP. As far as what we were able to glean from this most recent study, we were able to quantify the dependency on the solar zenith angle. So some people have expected to see something like this, but I don't think it's been quantified before. We've also found that the difference in the fraction of low quality versus high quality retrievals likely mediates the difference that we're seeing in the L3 products. As far as the cause of this bias, there's a few different possibilities. We could have some bias that occurs from the instrument not being sensitive enough to higher levels of attenuation that occur at lower solar zenith angles. We would call that a 1D retrieval artifact. We could have some influence from the signal to noise ratio for the CALIOP daytime product being sensitive to the amount of insolation that you have. Or we could have what we call a 3D cloud effect from aerosol, which just means that when the sun is passing through at a higher solar zenith angle, it's going to pass through more things before it reaches an aerosol layer. And so you have more scattering in more direction that creates more background noise. And of course, it's always possible that there's some combination of all of these things happening. And then again, I still haven't figured out yet the extent to which the reanalysis CALIOP AODs is being propagated from these passive sensors, but I think that going forward, that's an important thing to constrain. And then finally, just kind of some big picture things that I'm left with after this. So a lot of the work that's done at GISS focuses on improving model representations of these types of processes. But here, we still actually don't have the observations really very well constrained, and I think more effort could be done to kind of focus on constraining this seasonality question. If we have opportunities to get new observations. Hopefully we can use some of this information to help us do that. So we could perhaps target our observations towards the cluster 1 locations where we have relatively few observations so far. In the meantime, I think it's fair to say that I at least am pretty cautious about using any sort of reanalysis products to characterize Arctic aerosol seasonality. From everything that I see right now, I don't have a ton of confidence that they're getting it correct. And then lastly, because we've been able to quantify some of these dependencies, it may be possible to develop new data products or to apply adjustments to existing products and sort of get nudged comparisons between the different AOD data sets. And that's it. So thank you so much for having me, and I'm happy to have questions now.
Okay, sure.
We can go a bit over. Yeah.
Oh, great talk. Thanks. Can you go back 2 slides?
Yeah.
So the last, the one ahead. Yeah, so the last point, about the reanalysis Calliope bias. Okay, so it's either gonna be the assimilation, as you say, so you're speculating if maybe this propagation of the passive sensor biases, but it could also be the model. It's not simulating the transport. So one useful product is in relation to the MERRA-2 bias, because I'm not sure if these biases are also seen with other reanalyses that you've looked at.
I've only looked at CAMSRA and MERRA-2 so far. There's a paper, Ping's paper actually, where she looked at other reanalysis products characterization of seasonality in the Arctic, and they tended to kind of have this same structure where they have 2 peaks.
Okay, so the reanalyses are kind of similar to each other.
Yeah.
Okay, but at least for MERRA-2, there's a product, it's called the MERRA-2 AMIP ensemble,
Okay.
which may be useful to look at if you want to look at the contribution of the model bias to this, or at least rule that part out. So essentially what that was is that they took the MERRA-2 model and they did an ensemble of simulations, except without any data assimilation.
Okay.
Okay, so there you're gonna be having essentially what the model wants to do, you know, in the absence of the assimilation. Now, it's not gonna assimilate also the meteorological field, so then you're also gonna have that contribution too. But it would be good to compare maybe what the MERRA-2 reanalysis fields are to the results from that MERRA-2 AMIP ensemble, because that's also like a publicly available product. And that was used specifically to answer this question about the role of model bias versus assimilation in the generation of these biases that you see in the reanalysis products. So that's a useful thing. If you go to the GMAO website, it's called the M2 AMIP ensemble. I don't know if they have all the aerosol fields that you need, but certainly like AOD would be good to know. And then just a little bit more about that. So the assimilation in MERRA-2, because MERRA-2 did assimilate aerosol observations, was that just, so all that was just passive sensors that it assimilated, or?
It doesn't assimilate Calliope.
Yeah.
It does assimilate some AeroNet observations. My understanding is that it relies most heavily on MODIS, and that the other instruments are given less weight.
Okay. And then just one last comment. For I think it was cluster 1 that you had was like over the North Atlantic or something like that. You may want to consider too, just since you have a dearth, you basically don't have any of the ground-based, and none of the stations are there.
Yeah.
And since that does have that pronounced seasonality, you could consider also some of the measurements from the ATOM campaign, just because those are vertical profiles. Again, you know, it's aircraft, so it's hard to generalize and things like that, but those could be useful too to look at, especially because they went in that region.
I do.
Yeah, so that's the yellow region, right?
The Calliope.
Oh, cluster 2, okay, cluster 2.
But that is what you were talking about. You're talking about the higher seasonality.
Yeah, I was talking about the yellow line.
Okay.
Yeah, so it may be useful. I don't know how far north. I don't know if it goes sufficiently far north, but I think that there are measurements that go up there.
I think I have some downloaded, so maybe
There you go.
just on that note with the Calliope processing algorithm, it depends on classifying each aerosol layer as being a particular aerosol subtype. And then the subtype of the LiDAR ratio, which they're used from that to infer the AOD, depends on the subtyping algorithm. The subtyping algorithm depends on the location of the retrieval, and different subtypes are available over the land than are available over the ocean. So when I saw this like very distinctive clustering just over the ocean, that actually did suggest to me that that could potentially be a processing artifact. The reason that it's clustered like that, but I can't tell for sure from what I have here. Yeah.
Oh, great talk, Sarah. I have two questions. They're unrelated to each other, but just on this slide, can you remind me what you clustered, what variable you used for the clustering? Was it the seasonality itself or another?
Yeah, so I just looked at monthly median values for each grid cell, and then I clustered over that seasonality.
Oh, okay. Okay, so is there kind of like a little bit of spread or like at each of those points perhaps?
Yeah.
Generally has that characteristic seasonality.
So I didn't show this here, but I have another plot where I plot for each grid cell its Euclidean distance from the centroid of its cluster. And so that is useful for figuring out like which grid cells are like most representative of their cluster. If you were, for example, to use this study to determine where observations might be really useful, you could, for example, choose a point where you had really high or a place that's really close to its centroid.
Okay, cool.
Yeah.
Thanks. And then another question I have is, so I'm aware, correct me if I'm wrong, but that MODIS is not able to capture the AOD in the cloudy regions. And so I'm just curious if that's the case for the other observational data sets you used, and how did you take into account of like cloudy regions? I know you had a comment in your conclusions of looking at that 3D.
No, that's a really great question. So Calliope can retrieve above clouds in all cases. Through optically thin clouds, it can also get some retrievals as well. Because, let's see if I have, because the aerosol burdens, if you're looking just on top of the clouds, tend to be lower than in cases where you're just looking at like only clear sky cases. You'll tend to see that the all sky cases tend to be lower than the cloud-free cases. But here, at least in this comparison, I'm looking at both the all sky data set and the cloud-free data set. And so if you look at like VIIRS or MODIS, and you want to just look at the summertime values, you'll see that actually like from April to September, the VIIRS structure tends to correspond really well with the Calliope cloud-free structure. So that's a much more like one-to-one type comparison, and does give us it gives me at least some confidence that like the problems that we're seeing really are exclusive to the low light months, because they're actually like agreeing with each other pretty well when we're controlling for sampling biases, when we're controlling for cloud-free versus all sky cases. Yeah, did that answer your question?
Yeah, I think so. So like the structures is similar, but there's still kind of a difference in the scaling. So what would be the difference in the scaling between,
I think that's related to the global bias, the undetected layers with Calliope.
Thank you.
You only study the region is 60 to 70 degrees because in the winter you cannot observe the polar cap, right? So in the title you say the aerosol seasonality in the Arctic region. Do you assume the polar cap AOD property is very similar to this belt?
I don't think I can go as far as to assume that. I think I wanted to get as much as I could with what I had. If we look at the station data, you do tend to see the two stations that I have that are above 72 North tend to have a very similar seasonal structure. In conversations with other people, I've heard them say, well, actually, that because they have a much stronger seasonality, maybe the low Arctic stations actually don't have this Arctic haze phenomenon. What I've found from this, from the clustering analysis that we did, is that we actually do see, even in the low Arctic, a much more pronounced seasonality that we're seeing than what we are seeing from the stations in the low Arctic. I don't have anything that I can use, unfortunately, to get sort of a broader understanding of what the seasonality is on the high Arctic, but at least from what we've been able to see is that actually the low Arctic stations do tend to show a similar seasonality to both the high Arctic stations that we have.
Actually, the subpolar region, right? Subpolar region.
This
Subpolar region.
South Polar?
Subpolar.
Oh, the
That's-
subpolar region. So yeah, so that's part of the reason that we were looking at, we kind of dropped down from 65 degrees threshold to a 60-degree threshold, because we do have more observations when we go just a little bit below the Arctic Circle. And so what I saw from the clustering was that we didn't see like a latitudinal gradient that was cut off like at 60 degrees. It would be interesting to see kind of going a little bit further down from that, like when we start to see this seasonality being more and more pronounced.
Well, to that point, I mean, how much can just be interpreted in terms of the isotropic structure,
Right.
right? So if you just look at that dome, you know, when do you intersect those strong isotropes? So.
So this is really nice. It's also very sobering. As a model. So do you know like what aerosols are especially biased? You mentioned one of your clusters was in the wildfire zone. And maybe this is a question that's really about assimilation, but you know, how do the models drag the aerosol concentrations into agreement with the AOD that the sensors are erroneously getting? I mean, do they just invent aerosols in the middle of the transport, or do they change the sources or something? I mean, I guess I'm trying to get a sense of like as a modeler, like which aerosol species are the biggest problem, and which get projected onto these areas.
So yeah, so that I don't know. I am still in the process of trying to understand exactly how the reanalysis products do their assimilation. So where I am now in that is I did find one paper that talked about how it was assimilating AODs, but they didn't actually have, I was curious about whether they were only assimilating MODIS QC flag 3 AODs, or if they were also assimilating lower quality AODs. I reached out to someone at, I think it was Goddard, and who worked on the reanalysis product, and the feedback I got was that actually they don't assimilate AODs at all. They assimilate reflectances, and they only assimilate high quality reflectances for the MERRA-2 AOD product. So I'm still figuring out exactly what's happening. Where I was also pointed to, this might be, Susanna, kind of similar to what you were talking about, pointed to a data set that you can use where you where they show how much the like a priori AOD was adjusted once the assimilation occurred, and so that could also be a proxy for where you're having adjusted values and where you're not. The other thing is, even if this, so we saw with the reanalysis products that we had biases in seasonality that were extending well below the Arctic. So even if the Arctic isn't assimilating a lot of passive sensor AOD retrievals, if there's biases between the seasonality that are extending, below just the highest latitude stations, which in our solar zenith angle analysis, we think that there might be, that assimilation could in the lower latitudes could potentially propagate into the higher latitudes as well. So yeah, so I guess that there's just a lot that I'm still uncertain about with that.
Like CAMSRA, I don't know if they are also assimilating. I don't know that much about that particular model, but it seems like my understanding, I think I saw it like an AG talk a couple of years ago, where somebody was comparing, aerosols, Arctic aerosols in between CAMSRA and MERRA, and they concluded they were very different. They're probably both wrong compared to CALIOP, but it seemed like they were coming up with different errors.
Yeah, and actually Ping's paper talks about this. So CAMSRA is one that she points out because it just has much lower values in the winter than any other reanalysis data set. I still think that still think the CAMSRA seasonality looks more similar to the MERRA-2 seasonality than it does to the CALIOP AOD seasonality or the station data. So my kind of thinking is that, whatever is happening in the winter is probably affecting this reanalysis data set as well as the others. But that one is a particular data set where at least some people have pointed out that there may be some issues in the way that it's simulating transport in the winter time.
Thank you.
Okay. You don't see any questions in the chat, but if you're online, you're welcome to throw them in, or you're welcome to unmute yourself. Otherwise, we're getting close to the hour. So we can just give another round of applause to Sarah. Thank you so much. And then Sarah has said she can be around this afternoon. So if you guys wanna stop by, we'll probably be in 608, or I don't know if you're open to having meetings with people. Either way, Sarah will be around.